Hi everyone. In this video, we are going to talk about attention is all you need. In our last video, we have deep dived into transformer architecture where we have discussed about encoders and decoders. One of the other core component of transformer architecture is attention is all you need, and this is the complete paper that we were referring in the previous module as well. So in this video, we are going to deep dive into attention mechanism and how it works. Let's look at this example. The animal didn't cross the street because it was too tired. What is the purpose of attention? Before I talk about it and give you a brief about it, the importance of attention is contextual understanding and encoding. The contextual understanding comes from these breakdown of the sentence. If you look at this sentence here, the animal didn't cross the street because it was too tired. The question is how it refers, right? The self-attention process, when the model processes the word it, self-attention allows the model to determine that it refers to the word animal. This distribution of the words helps us break down the sentence, understand the context, and find the relationship between the surrounding words. In NLP terms, this is called as disambiguation, which is achieved by looking at the context provided by the surrounding words. The model assigns higher attention scores to the words that are more relevant to the current word, allowing it to make the correct association. As the model processes each word, each position in the input sequence, self-attention allows it to look at other positions in the input sequence for clues that can help lead to better encoding for this word. So self-attention enables the model to associate each word with the relevant context in the sentence. This is crucial for the task like, when we are doing translation, when we are doing summarization, when we are doing QA, question answering system. All of these cases, understanding the relationship between word and key is important. Word is the key. The other aspect I said, like by focusing on relevant parts of the input sequence, self-attention improves the encoding of each word. So this leads to better performance on downstream tasks as the model can capture nuances of the language. Let's look at self-attention in detail. Let's first look at how to calculate self-attention using vectors, then proceed to look at how it actually implement using matrices. So the first step in calculating self-attention is to create three vectors from each of the encoders input vectors. In this case, the embedding of each word. So for each word, we create query vector, key vector, and value vector. These vectors are created by multiplying the embedding by three matrices that we trained during the training process. So for each word in the input sentence, let's say I am feeding in a word cat. For each word in the input sentence, three vectors are created. What are those? Q, K, and V. Query, key, and value. These vectors are derived by multiplying the word's embedding vector. So that means we get this word cat, convert this into an embedding vector through a different algorithm, not part of transformer. So we get this embedding vector and multiply the word's embedding vector with three separate weight matrices that are learned during the training. And this can be presented as we'll see in the next slide, where let's say Q is calculated by getting the embedding vector multiplied by the weight of it. Similarly, k is calculated by multiplying the input along with the weight vector of it. Similarly, for v, it would be multiplied by input multiplied by the value weight vector for the value. So x is the embedding vector here in this case, and we are calculating the weight matrices by multiplying through it. So the dimension of query, key and value vectors are smaller than the embedding vectors. Notice that these new vectors are smaller in dimension than the embedding vector. Their dimensionality E is 64, while the embedding and the encoder input output vectors have dimensionality of 512. They don't have to be smaller. This is an architecture choice to make the computation of the multi-head attention. What does that mean? Is it can be more, it can be less, depends on what is the architecture design that we are building upon. So typically, if the embedding vector has a dimension of 512, then the q, k and v might have a dimension of 64. This reduction in dimensionality makes the computation of the multi-head attention more efficient. The higher the dimension is, the higher GPU memory you need and the higher computational power you need. If you look at this diagram here, I have input which is getting into an embedding vector which I showed you earlier, and that is multiplied by the query vector which becomes WQ. Similarly, it's multiplied with the key vector which becomes WK, and then it multiplied by the value vector which becomes WV. So multiplying x1 by WQ weight matrix produces Q1, the query vector associated with the word, and we end up creating a query, a key and a value projection of each word in the input sentence. So what are these query, key and value vectors? This is important and very important to understand what is QKV and where does it come from. So if you look at where the query vectors come from, there's two kind of attentions. Source target attention, which is encoder decoder attention, and self attention. Again, this all exists before transformers was proposed. So in the context of sequence to sequence models like transformers, these attention mechanisms, which are I'm talking about encoder decoder mechanism, allows the decoder to focus on relevant parts of the input sequence generated by the encoder. Decoder can focus on some part of the encoder generated outputs. So query that comes from the decoder current state, query comes from the decoder's current state, and key and value comes from the encoder's output. So here you get the key and value. This generates the question, that is query. So this mechanism is crucial for tasks like translation, where the output sequence needs to be aligned with the input sequence. For source target attention, where key value comes from encoder's hidden layer, that is source sentence, while the query comes from decoder's hidden layer, that's the target sentence. This is the encoder decoder attention we just talked about. So the other one on the right is called self attention, which we didn't talk about yet. The query, key and value all comes from the same place. That's why it's known as self attention. For example, the encoder, query, key and value all comes from the output of the previous hidden layer. So self-attention is used within the encoder and decoder layers. Within the encoder and decoder layers. Okay, so this is the source target attention and this is what we call self-attention. Alright, so in this case, you can see that I have two different, one is that is creating the source and value, let's say a key and value from the encoder, and then we have get the query from the decoder. In this case, everything comes from the same layer. So query, key and value all come from the same source. It can be an encoder, or it can be a decoder. Alright, so we will learn about this later on, that transformer architectures are either encoder or decoder based. For example, today's LLMs such as GPT are decoder only models. BERT is an encoder only model. We have encoder decoder model as well, like Flanty 5. Now the question is, if we have only encoder model or we have only decoder model LLMs, how are we getting this QKV? So in case of transformers, the QKV can be generated using self attention. In that case, you have the source only as an encoder, or it can be only as a decoder. You don't need decoder and encoder to generate this Q, K and V. So these are the two different processes. I hope this makes sense. Source target attention and self attention. Now let's understand how these scores are getting calculated. The score calculation happens by multiplying Q, K and V. So the score is taking the dot product of query vector with the key vector of the respective word we are scoring. And so if we are processing the self attention for the word in position 1, the first score would be the dot product of Q1 and K1. The second score would be the dot product of Q1 and K2 and so on. So we will calculate dot product between Q and K, and finally we will get a score. The score will be a dot product of Q1 and K1, Q1 and K2, Q1 and K3, so on. So the third and fourth are to divide the scores by 8, the square root of dimension of the key vectors used in the paper. So in the original paper, attention is all you need. Dimension is 64 and we do root over 64, which becomes 8. So this leads to having more stable gradients. There could be other possible values here, but this is the default. Then pass the result through a softmax operation. Softmax normalizes the scores too, so that they are all positive and up to 1, because softmax helps you range the values between 0 to 1, and this is what we are talking about. So let's say if you sum them up, it becomes, if you sum 0.88 and 0.12, it becomes 1, right? So we divided by 8 the whole value, and then we get this. So this softmax score determines how much each word will be expressed at this position. Clearly, the word at this position will have the highest softmax score, but sometimes it's useful to attend to another word that is relevant to the current word. So basically this score tells us which word will have more attention over the other word. So the fifth step is to multiply each value vector by the softmax score in the preparation to sum them up, and the intuition here is to keep intact the values of the words we want to focus on and drown out irrelevant words by multiplying them by tiny number like 0.001, for example. So finally we get the softmax score, and then we get the value, and then we calculate the Z score. So this concludes the self attention calculation. The resulting vector is one we can send along to the feed forward neural network, and in the actual implementation, however, this calculation is done in matrix form for faster processing. So let's look at that now that we have seen the intuition of calculation on the word level. Since we are dealing with matrices, we can condense steps 2 through 6 in one formula to calculate the output of the self attention layer. So if you look at this softmax, which is getting value of Q and K divided by root over dk, which is the 64 as the dimension, and we multiply it by the value which is giving us the Z vector. So the self attention calculation is happening through this matrix form. The scores are then passed through the next layer of the transformer, which is the last layer where we actually get the output of this model. So this is what is the complete flow of an attention calculation and attention vector. So this is our input sentence, thinking machine. we get the embedding out of that. So each word is getting converted into a embedding, and then we split into 8 heads. We multiply x or r with weight matrices, so we get each of the weight matrix in 8 heads, and then we calculate attention using the resulting q, k and v, right? And this is what is giving us the z score. So the finally we get a w0, which is w output, wo, to produce the output of the layer. All right, so with this we can conclude about attention mechanism and how does the attention mechanism works and what are the importance of the attention mechanism. As I said, contextual understanding and improving the encoding, which is basically leading better performance on downstream tasks as the model can capture nuances of the language. That concludes the attention mechanism. Thank you everyone for watching this.